Thanks everyone. I think had some cool tech talks this morning. And joining me, this is Matt from Morrison Fabrication. And we are going to talk about some awesomely fabricated manifolds, right?
Thank you. Yeah, and actually I wanted to, some of the stuff that we're really excited about, like really getting into, is thinking a lot about like some of the negative effects going on, and there are a lot. It might not be as glamorous as talking about like some of the above and beyond effects, but there's so many negative effects going on, and it affects such a wide RPM range, and there's different effects going on down low, in the middle, on top, and I think that's where you can really wrap your head around what a turbo manifold is actually doing, and how you can see it when you're tuning the car in the VE map, different setups, how they affect the engine, and looking at the whole setup as a whole. I mean, you can look at this and you can look at the turbine housing and the turbine wheel, but you can't quite find anything, so you have to look back at what it's doing to the engine itself, what it's doing to the rest of the setup, and then you can kind of grab your head around it. So that's kind of what I think we might go with it, but we can go wherever.
Sounds good to me. I mean, why don't we do this for the guys that are kind of new and newbies to the technology and stuff? Just in a real basic sense, what are some of the design considerations in a manifold that you'll put in there? Like, example, equal length runners, the length of the runner, the diameter of the runner. How do you, when you go to the drawing board and you guys are making these things, how do you guys kind of come up with your plan A that you build to, and where do you go from there?
Yeah, it's all application specific, and all those are definitely factors, and that's why we have so many product offerings, because there's so many different things to tailor it to. I could probably start with the runner sizing.
Okay.
We've done some back-to-back testing where we changed only the runner sizing. This is the more standard runner sizing, which matches really closely the exhaust port size on the 4G63, and it just seems the most natural. That's what you pick. We found it specifically for, like, I would say, like sub 700 wheel horsepower setups. That this isn't quite ideal. You can definitely use it, but you can often get away with a smaller runner size. And what we found, surprisingly, on that specific test, is it made more power. It of course spooled a little bit sooner, which was kind of expected, but it also made higher peak numbers, which was really surprising and just great to see. But you can match the runner sizing and sometimes get a net gain everywhere if it's just well matched. So yeah, well, that's a big thing, trying to match their. Where else should we go?
Well, talk about runner length in general. Is there benefits to have longer primaries or shorter primaries? What's your philosophy? What have you seen in your testing, and what do you try to do, I guess?
Yeah, so it's nice that we have this specific manifold, because on most setups, like last year we said runner length doesn't really matter, but it does, but in the sense that a lot of people think of it as far as like wave tuning goes. This is one of the few manifolds that you're going to package in the engine bay without going as a much more radical. But this one, the runner length starts to get more critical, where it's long enough where you can start to get some wave tuning effects. Okay. But even with this long of a runner length, those wave tuning effects don't happen until about 9,500 RPM. Okay. Most setups aren't going to see that, but like the larger setups like this, they will. So you can start to see that benefit, but that's already at this long of a runner length. If you want that benefit to be at a lower RPM, where a lot of people are going to be at most of the time, or ever see, you have to go even longer. And you're just not going to package that in most setups. You're kind of just going out of your way just to make it longer, and you're going to run into other compromises.
Right, because the further away are you losing some of that energy over the length of that pipe.
That too. I mean, you lose some of the pulse energy because it has to expand in that much larger manifold, and also the surface area is that much more, so you have that much more radiant heat going into the engine bay. Or if you want to package everything in one spot, you just have to have all these extra bends, which you're just starting to go backwards at that point.
Gotcha.
So it's definitely a consideration, but it's not something you go out of your way for. You try to package everything so you get the runner length that you want. You route it where you get things as close to equal, or at least comparable, because that can affect. There's a lot of different weird tuning effects going on in there, and that can affect any errant tuning effects where you have different cylinders seeing different, having different fueling requirements, because something we'll probably get into is, you know, the cylinders and the engine is actually pretty sensitive to what's going on the exhaust side. It's not just the intake side. Like, I think something that's been more known recently is like intake manifolds as far as the air distribution going into them. And it makes sense if like one cylinder is getting more airflow than the others, but yet your injectors are all delivering the same amount of fuel flow. You'll have some cylinders that are rich, some that are lean. You're only reading one sensor typically for the feedback to know like, okay, it's like 11.5 to 1, you're okay. But if one cylinder could be like 12.5 or leaner, and you just are running with it, you don't even know. But anyway, you're trying to make sure that all those cylinders are in much more equal airflow ratio or air fuel ratio, and that can it's just a nice peace of mind to keep everything as close to equal length as you can, just to avoid those negative things going, and again, another negative thing going on in the background.
So some of the things, let's talk about the flip side of this. Somebody purchases a manifold or has a manifold made for them. What are some of the things, I've seen certain things that go haywire, besides the thing cracking apart, falling apart. Let's just say the thing's holds intact. What are some of the issues they could have if it's a poorly designed manifold? And if you can't think of them, I'll help you out.
It's where to, so placement, I guess for when we're designing something anyway, I think placement is a big thing.
Okay.
Placement, and then the collector, you know, how shallow of a merge can you get away with and still be able to route everything and not have, like, you don't want to have to move the radiator or move power steering or all this other stuff for more basic setups when you can it just shouldn't be necessary.
Gotcha. Yeah, some of the things that I've seen, like on a poorly designed manifold, one is boost creep. You know, the way that they have the positioning for the wastegate and how that's working with the merge collector or wherever they have it. If you have a poorly designed manifold, sometimes it's just going to boost creep no matter what you do to it, and that's one sign you've got a bad manifold design. The other thing I've seen is, you know, things where you typically, for a certain size turbo and everything else you have on there, if you're not getting the boost response that you typically get or expect, you can also look at the manifold as potentially an issue there. Anything else, you know, with that you've seen? Or would that be pretty much it?
Could you talk about Wastegate Priority for a second?
Oh, yeah.
Because
Yeah.
that gets thrown around a lot. You know, oh, that's got bad priority. Oh, that's got too much priority. That's a big buzzword a lot of people like to use. But could you talk about that a little bit and how that affects it?
Yeah, so one of the big misconceptions, you would expect, I'll start here, you would expect that for higher boost, people typically like think bigger wastegate. But it's the opposite. It's because like what you were saying before, you know, when I forgot how you said it exactly, but like when the wastegate opens, does exhaust pressure go down or go up? But I mean, and it's tricky because you don't know which comes first necessarily, and also there's some other stuff I don't want to get into yet, but wastegate priority is very important because you want to be able to control boost within your target range, and I think that's the most important piece. Like, that is one of the things, like, what is your boost target? Like, for example, if you have pump gas, typically you're going to want a lower boost target anyway, and that's where wastegate sizing becomes more important. We might say, like, oh, if you have a 38 millimeter already, like, you might want to step up to a 44 millimeter just to be able to have that more surefire lower boost control. And another thing too, a wastegate priority is how gradual, is there a nice radius entry into that wastegate so it'll actually flow out of the wastegate, so it doesn't really want to turn.
Air has mass.
Yeah, mass, inertia, like, and something we address a lot, again, that target boost range, and like this doesn't have, on this setup specifically, it doesn't have like a really nice radius entry, because you can't, I mean, there's nowhere to get a nice radius entry. But in this, you have two wastegates, you're going to be running higher boost anyway, so you can get away with it. You could change the design to have a better angle of entry to the wastegate, but as long as you can control it within that target range, you're not gaining anything.
Right.
So you could make it so
You're
the
compromising packaging in order
Yeah.
to do something that you don't need.
and you could do it. the wastegate will just open less.
Right.
Which, I mean, the thing that I'm sure we'll talk about is that dry pressure to boost pressure ratio. That ultimately decides like the characteristics of the setup and like the power it's going to make for the boost and stuff like that. Having a better wastegate entry angle isn't going to change that ratio. That ratio is based off everything else. All the wastegate does is it bleeds off that exhaust drive pressure to then lower boost pressure.
Well,
might say that last bit a little bit.
All the wastegate does is bleed off.
Yeah. So the main thing that the wastegate does is it bleeds off exhaust pressure, which would usually go into the turbo. That bleeds it off to lower the drive pressure, which then lowers the boost pressure to your target range. If it can do that, and if it can control boost where you want it, the wastegate sizing fine. You could get a larger wastegate. All it's going to do is open less. So like, essentially, you kind of want most of the exhaust going into the turbo anyway. The wastegate's just to lower that. But obviously, like if you can't lower it enough for the fuel that you're running or for the setup, like larger, more efficient turbos typically need more boost control or larger wastegates or more priority flow. And that is definitely something that on most of our stuff, like we already, where we can get away with it and have like a really nice angle of entry, absolutely, we do it. But we're not going to go out of our way when there's not going to be an actual benefit to it.
Right. Makes sense. Because you're kind of looking at the thing as a complete design and checking off all the boxes and to make that work better when it doesn't need to work better, and giving up the packaging and how it's going to fit. It's just not worth it.
For the driver's seat, it's not going to change anything. Like
exactly. I mean, you still want to be able to access the bolts that bolt the flange to the head. You know, I mean, so those things are all a consideration. Okay, for sure. Go ahead. Was there a topic you wanted to start with, or?
I have a lot of things I could get into, but I don't know.
Yeah, so let's ask you guys. Yeah, sure, go ahead.
When do I need a 2-inch runner?
2-inch. This is just a little bit under 2-inch.
People always want to go, I need really big. Like, at what point is that for real, that you really do need really big runners? Like, what power level? You know, like,
I don't even
over 1,000? You know, those are not common.
I don't think there are any setups, even on the most extreme setups, that are doing that have that size runner. I mean, typically the runner size will also step up with the RPM range, and I mean, how high are people going? Like, I haven't seen an application where necessarily you want to match it to still have a lot of port energy. It's not just bigger is better, because you want to keep the port energy, and ultimately at the end of that exhaust stroke, you want to be able to continue pulling on the cylinder, get the rest of the exhaust gas out, and then that's where you get the gains.
And all of that, you know, it's really dependent on the cylinder head being attached to it too, because how important is it to have a 2-inch hole here if the area of the port is, you know, closer to a 1.5 inch or 1.6 inch, you know, tube. One of the things I've noticed in seeing a lot of the engines come in, the more modern engines are getting smaller and smaller exhaust ports, and they're just becoming more and more efficient, especially if it's on a turbocharged application. They're keeping that velocity up as high as they can, because
some of them are getting fewer ports too.
And fewer ports even. Yeah, I mean, that's not the way I'd like to go, but it's still, you know, something to consider, because unless there's a reason for it to be that big, you're trading off, you're making a compromise, you're not actually getting a benefit. But that's just the American way.
Yeah, bigger,
you know, sometimes. And you know, you're gonna see a lot of misengineered products that are bigger and better.
Yeah.
You know, I see it all the time, you know, with the good old boys machine shops and what they're doing. We're gonna put 1/2-inch head studs in this because we've always put 1/2-inch head studs. And it's like, wow, well, you're better off putting a 12 millimeter in that, you know, taking the 11 to a 12, keep the thread the same, make everything nice. You don't have to mess with the head, use a better alloy, and it's a better solution. But nope, they're gonna put a 1/2-inch 13 head stud in it.
And with double the torque too.
Yeah, and it's like, all right, good luck, you know. But anyway, sorry, off topic, but yeah.
Bigger is better, like as far as typically post turbine, like you want to. Like,
yes.
It's important that afterwards it's just a mass flow. It's not like you're dealing with pulses. So you know, inlet conditions, bigger is typically better. After the turbo, bigger is typically better. But on this stuff, you're dealing with actual exhaust pulses. And when you're thinking about like drive pressure and back pressure, and we're always looking at those gauges and what that value is, you know, that value is an average. There's a ton of like peaks and valleys going on, and something we get into, I don't know about yet, but like that's what a turbo manifold does, is it manages those peaks and valleys and makes it so, you know, when it's most critical, it's not going to see those peaks. And I don't even know where to start there. I think we can
Do we have a question? If not, we can, we talked about kind of the overall design, you know, choosing the runner lengths, choosing the runner diameters, positioning, and you know, worrying about the wastegates and the transition, and then and all that for the boost level and the application and everything like that. Above and beyond that, I know a lot of what makes your manifolds different is right here, just on that entry, that transition, and thinking about, okay, what is this thing being bolted to? And really thinking about, okay, that path out of the cylinder head into the manifold is pretty important, not to have, you know, voids and weird transitions or ledges or whatever. How do you guys accomplish that? Because you do something in the manufacturing process to kind of get that transition to work as best as possible, right?
Yeah, so something that we have stuck with, and that we've done some cutaways of cylinder heads, of cutaways of the exhaust port to see, you know, that transition from the valve and the throat and the you know, and afterwards. And then putting different flanges with runners welded to them and cutting those in half too, and looking at, you know, what does it look like from the port to the manifold itself, because just because there's a flange there doesn't mean it's not immediately not important afterwards. It's one continuous piece that the exhaust sees. And we specifically use an oval port exhaust flange, where it forces you to form the runners to that oval port. And what falls out of that is you have a nice, when you form that runner, you have a really nice smooth transition from the port to the runner. Not only for when the runner is really well matched to the port size itself, you can get that oval to round, but also when you have stepped down to a smaller primary runner size, you can not only have that nice oval to round, but have that transition to the slightly smaller size and do that all really smoothly. And a lot of the things that we've seen is that it's really important right off the port,
Right.
for, you know, what's going to happen and what direction things are going to move when it is most important.
So would this be kind of the number one area that affects the performance of the turbo manifold, and then second would be the collector, or would the collector be more important, or how would you?
We've thought about that a lot, and it's hard. It kind of all adds up.
It does.
So I mean, you want to keep the exhaust moving, keep it moving in the right direction. Like at the collector, when you're lofting it across this void and where everything's merging together and you're lofting it across, is it going to run into a wall? Is it too steep where it's going to run into the turbine wall, which is tapering down? Is it going to run into that, or is it going to go straight into the turbine wheel? Is it going to rely on just, you know, its existing velocity and momentum to get it where it needs to go, or are you going to have to rely on additional pressure to push it where it needs to go? And obviously you don't want to do that, because, you know, that kind of pressure, relying on that is not ideal. You want to keep things moving, let it just keep moving through the manifold, and especially off the port, keep things just, that's where we've seen it's been really important for to see some of those volumetric efficiency gains, where specifically at the end of the exhaust stroke, where there's not as much piston speed or anything like that, where that exhaust can continue pulling and then get that last remaining bit of exhaust out, which then the intake stroke comes right afterwards. We can get filled, instead of having some residual exhaust gas in there, you can make sure that's filled, some scavenging, which actually, scavenging and residual exhaust gas, we've thought about that a lot. Like, which one is it? Is it like, is there a scavenging effect, or is there a residual exhaust gas? They're kind of two sides of the same coin. The only way you can get that scavenging is if you have a depression left in the cylinder, or a void for that intake air charge to fill. So, you know, you get rid of that exhaust gas, and then you just have more area to fill on the intake stroke, and essentially that is like making, if you don't have that, the engine's acting smaller. If you have exhaust gas that's remaining in the cylinder, it acts like a smaller engine. Whereas if you can replace it with fresh intake air charge, it can literally add, you know, 5, 10, 15, sometimes 20% extra volumetric efficiency, which acts just like engine displacement, which not only makes more power per PSI, but it also has more mass flow going through the turbo, which can also light the turbo up quicker. So like, if you can do that, like, you have everything. You don't have to choose, like, you don't have to necessarily, you know, go, not a good analogy, but sometimes when you go with a smaller AR to get things to spool up quicker, you get more back pressure. But if you can just increase volumetric efficiency, you can not only get that quicker turbo response, but you can also make more power per PSI at the same time. So I think that's where it gets really exciting for us, is like, getting everything without having to compromise. Should I not do the same?
No, that's fine. I think I've saw it once. Place where you have no problem.
So, you got me convinced that you got the mojo when it comes to getting out of the head and out of the collector and into the turbo. I'm sold. Tell me about strength, durability, and what are your recommendations when it comes to supporting the turbocharger? I think I think a lot of times people will have headers and they don't take any extra efforts to support the turbocharger. I'm interested in your thoughts on that.
Okay, yeah. So on a lot of like the really thin wall, large online wholesale retailer folks, brands, they will have like a brace on the manifold itself. But the issue with the brace is the manifold moves with heat, especially stainless. Once it gets up to temperature, it's going to try to move, and if that brace isn't going to heat up as much as the manifold, or it's not going to yield in a certain direction. If the manifold's trying to go that way, something has to give, or at least something's going to fatigue and then fail. So the brace can work against you. It can help for like engine vibrations, but as far as thermal loading and thermal expansion and contraction, something eventually is going to give. So a brace could actually cause a failure.
So ideally, the manifold's engineered in such a way that with the turbo on there, with everything fitted on there, when it goes through its normal heat cycles and stuff, it's not fatiguing over time, and it's gonna give you a lifetime worth of
so like
crack-free performance, basically.
We always use Schedule 10, and it is 321 stainless. We switched to because it was just available, and it just gives us extra peace of mind, even with the thicker wall material. It's just nice to just still go that route where you don't need any bracing, especially for like these setups. If you have like a forward-facing setup where the turbo's way out there, you might have a brace, but that brace is going to be pretty much just supporting the weight of the turbo, and it's going to have like a hind joint perhaps.
Where go back to the motor.
And it's going to help support things, but it's not going to like hold things tight because you got to let things move a little bit. So, but I mean, there are applications where brace would make more sense, where you're trying to fight like engine vibrations more of a factor than thermal loading and things like that. But on most instances, you'll more want to think about like the rest of the exhaust system to make sure you actually have exhaust hangers. So you're not trying to hang the whole exhaust with it.
The weight of the whole exhaust. Like a lot of times people delete all of that. Like the one right by the oil pan, like that's important. I could take the heck out of there, right? We don't hang that 20-pound downpipe right on that turbo and right on that header.
They have one hanger at the muffler. But also having a flex section on a transverse engine, the engine twists kind of no matter what you do. Have a flex section there, especially near like that fulcrum point. So you're not putting all the stress not only on all the studs and on the head, trying to hold everything and like fight that engine torque, but have it able to rotate there to kind of reduce the additional stresses that would be there. So I think that's more important than trying to like think about specific braces. You can do it, but it would be a very specific type of brace, and we try to on a lot of our stuff that we offer, like it doesn't.
Not necessary.
Right.
Okay.
So you mentioned having different air-fuel ratios, cylinder to cylinder, and one of the things that's starting to make a comeback that I've seen on it seems like the smarter racers out there that want to have the things live is going back to having individual EGT sensors per cylinder. Is that something in your design that has been considered at all, like that positioning or access or anything like that?
It's something we can add.
I mean, because on this particular manifold, it really seems like it's not too bad.
We don't necessarily design the manifold around those, but we haven't run into a setup yet where you can't fit them.
Okay.
And I mean, we have an entire test stand and engine setup, and then typically use that exact turbo where we can find, where that ideal placement is, where you can access it. It's not gonna, you can get to everything still. And also, it's really important to have the same distance from the port itself. Try to make sure that the sensor's in the center of the runner itself, to make sure you're not you know, make sure it doesn't look like one is leaner, richer, hotter, cooler, just because it's in a different spot in the runner.
Gotcha.
So, something we can do, and something that is really nice, just to, when you're pushing things near the edge, or if you have an injector that's, you know, starting to get a little clogged, anything like that, you can catch it ahead of time. And again, since there's only one sensor, typically O2 sensor, it only knows what the average is, not what each cylinder is doing. It's not always necessary, but it is a nice peace of mind. Or even people do the individual wideband bungs too. Those get a little trickier to package, but we've done those before too, and those are nice to have because the EGTs, they take longer to, like, you don't have is high of resolution. There's a latency before it gets up to temp, so you could have that cylinder lean out and not catch it with an EGT, but with the wideband you could.
Well, a lot of people don't think about also on EGT probes, you're gonna put 4 EGT probes on there. Like you're talking about, generally they're slow responding, so they don't give you really high frequency data. EGT probes where they're open tip, where they can be faster or lighter weight, then what are they? They're more delicate too. So those things will start to, you know, after so many hours, they'll start to melt, break, fatigue, and where are they going? Yeah, they're gonna go to the blender. So,
Let's see what else.
can we pass that around?
Age-old question, post-turbo or pre-turbo wastegate, or just simply depends on setup, place, you know, or personal preference?
You would be referring to like on like a
Like running a gate off a manifold versus running it off O2 housing.
Okay, so
Yeah.
like a DSM specific,
Right.
or you mean Evo specific
Or even
too?
Evo or
Actually,
Evo.
there is something I want to get into on the Evo specific stuff.
Okay.
But yeah, for yours,
I mean, I know it gets talked around, you know, there's a lot of
Yeah.
guys that, age-old argument, you know, what's better, what's not better.
well, you don't want to have it off a single runner. There's some I mean, it works, but you don't want to have it off a single runner. There's certain cast manifolds where it's off runner number 1, and you're relieving the drive pressure on that one single cylinder. So once that wastegate opens up, that cylinder has less drive or back pressure that it's seeing, a small amount, and it's different, and then that again can affect the cylinder to cylinder. So you want to have it pretty much after all the runners have joined, and that's where you want to have the wastegate. So technically, there's not much difference between having off the collector and the turbine housing. It'll just change like the angle of entry or things like that, but it's not necessarily going to. With the DSM stuff, I don't think there's a reason to try to aim to have it off the collector versus off the turbine housing. I'm sure Robert would.
No, I think you're exactly right. And to answer that question, it's essentially the same.
Yeah.
Whether you have it in the collector or if you have a DSM, like an OEM style DSM housing, and you've bored the hole open and you have the wastegate on the O2 housing, that's still the collector. So that's not different. That collector is that whole region there prior to the first cross section of the volute, which would be another inch or so below that. So whether you have that, you know, an inch above the first volute cross section or 2 inches or 3 inches above it, it's kind of doesn't matter, right? If it's in the collector and it has adequate priority, or if it's in the turbine housing and it has adequate priority, it's doing the same job. But what you pointed out about the manifolds that'll have, like we used to weld a flange onto a factory manifold on a number 1 runner, does terrible things. You know, that one cylinder does not run like the other 3 cylinders, you know? So you're exactly right.
I think a big. I don't know if I want to get into that stuff yet, but I do think it's a good time to talk about the Evo2 housings, because some people, I don't know how common it is, but they'll want to run higher boost on like a bolt-on setup. So what they'll do is they'll go with an external wastegate, and they'll just they'll take out the flapper itself, and it's a factory divided setup, and then they'll have the wastegate off the O2 housing. But what that flapper's doing is it's covering 2 scrolls, because it's a divided setup.
Yeah, it's maintaining that pulse isolation.
You're isolating them, and when you open that, you can have crosstalk in the O2 housing before it gets.
That.
Yeah, so I mean, we did a very similar test where we allowed crosstalk or we shut it off. It was a very similar thing, and it was noticeable. Even just driving around to go and do the test, you could feel it, which was really interesting, and it richened up, and it lost volumetric efficiency. You felt it because the engine acted a little bit smaller, and I you already said it richened up, and the RPM, the boost threshold that it reached a given PSI, and also
Simon says good.
also the time it took to get up to, you know, it was like between like 5 seconds or 7 seconds.
Right.
It slowed it down by like 2 seconds. But that same thing can happen on an Evo2 housing if you do that. And I think there's really good intentions there to be able to hold more boost, but I think maybe I'd have to think about it more, but maybe in that case you'd want to keep the flapper there and maybe that opens still, you know, to control the boost where you want it, but or it's being opened by the exhaust pressure itself, which I think is something that the wastegates not only opens from the diaphragm and lifting it from the boost boost signal, but also it gets helped pushed open by the exhaust pressure. If that exhaust pressure gets really up there when you're trying to like push like a stock frame turbo, it can actually blow that flapper open, or an external wastegate depending on the spring pressure. But just have that, if you're going to do that, just maybe have that external wastegate off the O2 housing as an additional thing to hold boost.
Wow, I
You
never
know what
even
mean?
thought of that. Leave
Yeah.
the internal in there to keep those two channels isolated from each other and don't let them crosstalk, so to speak, like you're saying. But have the external capping that port, so that at the upper RPM, you can increase your drive pressure
Yeah.
as necessary with the external. That's interesting. I never thought of that.
But I'd rather see it done before I suggest it. Because it could be something that's not being thought of. But
Right.
But I think that's definitely a thing there, and I think that maybe some people have done that and noticed like the car's a little less responsive, or maybe it's like the tune changed a little bit.
Right.
And that's again something where that's that native cylinder to cylinder interference, especially at lower RPMs.
So maybe we can talk about, or just kind of explain, how many people understand completely why there's a debate, or why people think about a single scroll versus a twin scroll, or a divided inlet versus an open inlet, whatever you want to call it. Does everybody know exactly why that's done, and what the intent is of that? Okay, we'll just do it real basically. If you look at a 4-cylinder engine, you know, there's a 720 degrees of rotation, meaning that crankshaft's going around twice, and you've got 180 degrees of cycle for each of the 4 strokes. You've got an intake stroke, you've got a compression stroke, you've got a power stroke, and you've got an exhaust stroke. And that's happening over 180 degrees. Well, when you've got 4 cylinders, that's happening, you have an exhaust pulse happening every 180 degrees. So every crankshaft rotation, if there was no, in a perfect sense, if the valve exactly closed here and the intake wasn't still open and stuff, you'd have a perfect pulse for 180 degrees coming from each cylinder. That doesn't happen. The valves are actually open a little bit before and a little bit after, and it really becomes more of a factor, a lot of it based on camshafts that are being used, the engine RPM level, like Robert alluded to earlier, where these pulses, instead of being able to kind of use all of their power to push this to go to the turbine and deliver all that energy, sometimes they're overlapping, and there's, instead of it seeing, you know, a nice path to the turbine, it's seeing some restriction in there because of things happening. So the concept is, with a twin scroll, now instead of having 180 degrees between these pulses, because we're picking cylinders that are firing 360 degrees apart, now we don't have that crosstalk or that interference happening in there. You know, you've got this cylinder coming and it's done doing its whole exhausting before the next one's doing its exhausting. So these pulses are not competing with each other in the limited space in there. So that's the reason behind why they would do that. Now, on a 3-cylinder engine, like you're gonna find in the GR Corolla, there's no advantage to it. It wouldn't do anything. We wouldn't even know how you would split the 3 cylinders in two scrolls. Or an inline 6 twin turbo, there's no advantage to it. But on an inline 6 non-divided, you've got a big issue there with everything happening only 120 degrees. So it's even a worse issue than a 4-cylinder that you're going to have those challenges in. And we were talking earlier, one of the things you noticed is when you do go to a twin scroll, in that application where you're getting that benefit, in that RPM range where you're getting those benefits, the engine actually is behaving like it's a bigger engine. You're getting bigger volumetric efficiency, and yeah, kind of go from there.
Yeah, so, and I'll touch back on what's happening. So there's something happening on the turbine side where you kind of line up those pulses. But as Robert said, that effect really decays away in a lot of the RPM ranges that everyone's running at now. You know, on the factory OEM stuff, they spend a lot of time thinking about that RPM range, like 4,000 sub. But when you go, what's still happening is you have one cylinder in its exhaust phase, and then you have the cylinder that's firing right after it. One's still open, the exhaust valve's still open a little bit, just finishing exhaust phase, getting like the last little bit of exhaust out. And then you have the cylinder firing right after it, just having that really high pressure exhaust pulse enter into the manifold while that other door is still open from that exhaust valve. So what can happen is it can travel through, down the runner, up the collector, and then shove some exhaust gas back into that cylinder.
Or just not even let it come out.
Oh yeah,
Just not let it come out by one, or shove it back in.
Shove it back
Yeah.
in. Also, there's on setups with more aggressive camshafts, more overlap, you'll also have the intake valve open. So not only can it shove it back into just the cylinder, but it can shove it all the way back in to the intake manifold. And especially at lower RPMs, when you have a larger window of time for that exhaust pulse to make it all the way there. And a lot of things you can do are have slightly longer runner length, where you have a longer path, so it takes longer time to travel. So that makes it so you can get out of that negative cylinder to cylinder interference sooner, or at a lower RPM. So that's where you have, from what we've seen, like, or at least our reasoning is like, of why does a longer length runner tend to help lower RPM on the exhaust side. Like on the intake side it makes sense because you have that pulse tuning you can work with, but on the exhaust side, like we just said, like we don't have a wave tuning effect per se. Like it's not long enough to do anything. So how can a slightly longer runner length help with the volumetric efficiency improvements down low? Well, it just makes a longer path, so you can make it so it can't get to the other cylinders and have that negative cylinder to cylinder interference. So you don't have that exhaust gas getting shoved back in, reducing the amount of intake charge that can come in, etc. So that's one of the things you can do. You can also let the exhaust keep moving on its own. That'll help kind of shield it from the offending cylinders. You can make sure that collector is an actual collector and not just, you know, within the factory space constraints where they kind of like just point at each other instead of, you know, into the turbo. So it has a harder time like going like 180 degrees back into another cylinder. Like instead of being pointed at the other cylinders themselves, like it's pointed at the turbo. But also with an open versus divided setup, that's what you can just cut off that path completely. So those cylinders that would have the exhaust valves open at the same time, where one's going to be just having a high pressure pulse shooting into another cylinder's just hanging open at the last minute, like you cut off that path completely, and that's where you can get still those volumetric efficiency improvements. You can cut off the negative effects there. So there's length there, you know, open versus divided, having everything guided and directed where it needs to go. All those are working together, and it gets even more important when you have higher duration camshafts and more valve overlap. You just have a larger window, and it extends up to a higher RPM range where you can have those negative effects. That's like why typically camshafts will have, it'll just get soggier down low, it'll just be more finicky. But doing all those things can help make it much less sensitive to the camshafts, and you can like go with the more aggressive camshaft to get more flow, but be able to clean it up where it's not having those detrimental effects. So you can just work your way up.
In the most basic sense, you know, we're probably talking up here, you know, about all this
I have
stuff.
a hard time like conveying this with noises.
Right. So for the guys that are out there that are just thinking, okay, should I invest in a properly built exhaust manifold? I know you've done a lot of testing. You've tested some of the stuff that's out there. You've probably tested prototypes just to see how bad doing this or how good you think this is going to work, and it hasn't worked. And you know, you've learned a lot over time. Take an engine, you know, a 4G63 running, 25, 30 pounds of boost.
Just wait.
You can stop there.
Okay.
So if we look to make an apples to apples comparison, we've got a 4G63 engine running 25 or 30 pounds of boost on our test. From a poorly designed manifold to a well-designed manifold, what differences are you going to see in terms of response, in terms of peak power, and in terms of power, just the overall shape of the power curve beyond peak torque and stuff? What have you seen?
A lot of what you'll see is power per PSI. The poorly designed manifold is going to make more, or require more boost to make the same power. And what we've been talking about is when it's just a manifold change alone, if you're changing from a more poorly designed manifold to a better designed manifold, a lot of that difference comes down to how much remaining exhaust gas is in the cylinder. It's not 100% that's what it is, but like that's a big part of it, and that's like the mechanism behind it.
So you're going to make more power
At less boost.
At less boost, but it's going to be a lot of it dependent upon how big those cams are, because if you have bigger cams, you're going to see a bigger gain
More
with a better manifold.
Yep.
Gotcha.
Yeah, or it's going to be more detrimental. Like if you try to run like a really poor log manifold with really aggressive camshafts, like it's going to do really poorly.
Gotcha.
Where you can get away with it, like camshafts that are like really modest, where it doesn't have much overlap and it can get out of that negative range.
Mhm.
But I mean, it's you're working your way up,
And numbers wise, how much? Okay, if it's a 500 horsepower engine, and your manifold is able to get there at 25 pounds of boost, a poor manifold will require how much more than that? Would it be 30? Would it be 35? I mean, what have you seen?
So that's interesting. So I can talk about all this stuff, all these effects going on in the background,
Mhm.
but you can actually see that there's like 3 or 4 PSI, even on like. So a lot of the manifolds we'll test against are the FP race manifolds, because those are like the standard and they're really well designed. But they're still working within some cast I don't want to say limitations, but like working with what you've got and the constraints there. Whereas when you can open up the design, what we've seen is like a 3 or 4 PSI difference of like even at, I'm trying to think how to say it, so like the same power, it'll just require 3 or 4 PSI less.
Gotcha.
Or it'll max the turbo out at that much.
So we did the same thing, and nothing to dog on Robert, because we love Robert, we love your turbos.
Go ahead.
From his manifold.
Those manifolds are not perfect race manifolds. That's totally a compromised thing. So
They work great.
The difference between the cast performance manifolds and these is night and day.
Yeah.
They're not in the same category
I
really
went
at
from
all.
it, well, my FB Black went from his cast to his bolt-on tubular, and it was same time, same power, 5 PSI less.
5 PSI. Okay.
And I mean, didn't you say that it got in the stall a lot easier and was
It
able
was a lot
to
more
Yeah.
range
Yeah.
power.
like just with, I mean, I'm not trying to like, it just gets me excited though, but like you just change the manifold alone and you were able to get it on the stall a lot easier, which is awesome. Like, I love that.
Yeah, the drivability and mid-range power was significant.
Like, it's being able to see it from the driver's seat, a difference is just really cool. Like that's
Well, some people might ask you, well, so what? So it still makes 500 horsepower, 30 pounds of boost, 25 pounds of boost. What's the difference? Well, the difference comes down to at 30 pounds of boost, there's more exhaust back pressure. There's more residual exhaust gas left over. There's a hotter chamber temperature.
Yes.
So the charge air that's coming in has a hotter environment that it lives in, and as a result, you can't run as much timing. So I would beg to differ that you're going to make the same power. Quite commonly, you'll end up being able to make that power easier. You'll be able to add more timing, and you'll be able to make more power. Now these are subtle effects, but that scavenging effect and getting that chamber cooler, not having that BTU backup in that chamber can be big when it comes to tuning. If you don't change the ignition timing and you drop the exhaust manifold pressure by 5 PSI, you just left it on the table. You didn't take advantage of the thing you fixed. So.
yeah, or it will let you change.
If you do that test and you don't change the ignition timing, you're leaving something on the table, is what I'm saying. So you put the better header on and you go, wow, look, we made the same power. Great. Now but you already have the ignition maxed with the compromise or limited, restricted exhaust manifold, because you had that thermal load in the chamber, and that's as much timing as you could run. But when you get that chamber cooler by letting it exhale better, you get to add timing, and you get to make more power. Not just drop the boost to make the same power. In a lot of cases, you can advance the timing and make more power.
Yeah, that's what's hard with the back-to-back test, because you don't want to change that other stuff, because then like.
But then, as I say, it's not a fair test. You change the timing.
Yeah.
Well, I changed the timing because I could.
Yeah.
Yeah,
And the thing I'm trying to do is make power, so I'm gonna. You know.
Yeah, so I mean, or you could go with a more aggressive camshaft and then,
Yeah.
or bump up in compressor size or
Yeah.
turbo size and still have it act like the old setup with slightly smaller turbo. So you can make it, I mean, it depends on what the next step, smaller, larger is, but you can make the next step larger turbo that has that much more compressor flow, but make it act a little bit more like the next size down, which is again really cool. I mean, and you're right. Like, I think it's real important that like the power depends on the turbo. Like the turbo compressor flow is the limit, and a turbo manifold.
You can do a test where the A test had the turbo at 105%, and then the B test has the turbo at 105%, and you could have improved a bunch of stuff, but you didn't allow the possibility to see any of the improvements, because in both cases we can run 600 CFM. So
Yeah,
so
right.
you can design tests that
Yeah.
you'll never be able to show the benefit of your part if the thing that's maxing it out isn't what you're testing.
Yeah, at the end of the day, the turbo doesn't know what
Yeah,
engine
it
it's
does-
on,
right. Yes.
and it's
Yeah.
going to make 600 horsepower. It's going to make 600 horsepower. Where the parts come into the play is how soon can you start making 400 foot-pounds of torque, and how long can you carry 600 horsepower
Power
out
band,
here?
yeah.
You know,
Right.
and that's what's going to win. And you know, it's that
Power
area
band.
under the curve, yeah. And can you do it? You know, what's more impressive to me is not some guy who built 1,000 horsepower 4G and he has to run 60 pounds to get there. Is the guy who's been able to do it to run it at 48 pounds. That's pretty damn impressive. You know? That's impressive. Woo, no lift. Oh, it's clutch.
Your clutch didn't hold that.
I love how we all just.
Yeah, right.
Sorry, squirrel.
But yeah, that's, you know, a lot of times people, you know, making 1,000 horsepower engine with a big enough turbo to me isn't impressive unless you tell me more about it. You know, you're able to do it with this size engine, and you know, you're basically achieving this level of volumetric efficiency. Oh, you got a pretty good setup, you know. If you're just keep cranking up the boost until you reach the peak number on the compressor, who cares? You know, but you know, in this world, I mean, people are, you know, you're more often here, well, how much boost you run? How much boost you run? It's like, boost is the measure of the pressure of the air not getting into the engine.
It couldn't be it, right?
You know, so you've got a
really
problem.
wouldn't want boost. You know?
Yeah, exactly. But okay, so back to what we were talking about with the manifold. Now, on your setup, was that a twin gate divided? It was an open.
Just a single.
Yeah, it was.
Open.
And I went to their single.
And you went to single. So that was single. So I wasn't even.
Gates off the O2. Yeah.
Yeah,
Okay.
that was a stock DSM placement. That was
Yeah.
just the manifold change by itself.
Wow. Wow.
And later on, I did add a couple degrees of time to
Uh-huh. And did you see an improvement there also?
it. Yes.
Oh, yeah.
Oh, yeah.
Yeah.
Very cool.
That ran a.
With the old,
Am
we
I not-
just changed the setup, and it's a heavy car, not heavy, but it ran a 10-0
I was about to say you had a 10.0. I don't 130.
at 30 pounds of boost.
Yeah, that's awesome. Like.
Very cool.
Hard to argue with that.
Do we have any other questions?
$10 raffle turbo.
Oh yeah, that is.
Yeah, that's right. True turbo.
You won the raffle a couple years ago.
That's awesome. Do we have any other questions or areas? Yes.
Yeah, regards to the manifold coating, like specifically the inside of the log where you coat them in, because if some people do that, what are your thoughts on coating the inside versus the outside? What
I don't-
is the benefit?
I don't have, so there would be a benefit, but I don't have any direct experience. I've heard that coating, they have a hard time getting it to stay, because if it comes off, it's gonna go into the turbo. And how do you get something I have no idea about? How would you get it completely coated on the inside and also know that it's not gonna come out? I feel like if it comes off on the outside, like, you know, it sucks, but like it's not going into the turbo. So if they can get it to stay and they have all that figured out, I think it'd be great, because you're not only, you know, having a barrier for heat, keeping it in from going into the manifold itself altogether. That's great. But if they have the rest figured out, then sure, I'd be all for that.
How do you feel about the coating in general overall of the manifold? Have you done any testing?
So something we actually keep in mind during some of that dyno testing is how hot the manifold is to begin with at the start of the test, especially on manifolds that have a longer runner. Like that one, for example, we did a back-to-back test with a different design, and on some of the pulls, we had to consider that, like, how long was it since the last pull, and how hot was the manifold. If the manifold's like dead cold and you start to do a pull, you're gonna see it's gonna look like a much lazier setup, because a lot of that heat, instead of going into the turbo and driving it, it's gonna be putting energy into the manifold to get it up to temp. And there is definitely an effect, and something that'll show up on a dyno. So you don't want to get led astray by that, so you want to keep an eye on that. But then that comes into, you know, heat management with coatings or wrap or a heat shield, where that can be where some of those, it can be very beneficial. Not only keeping heat out of the engine bay, but keeping all the heat and the energy going into the turbo. It's a very, like, it's not like a wishy-washy, like,
Yeah.
it could be, like, it's there.
Yeah, I can add a little bit to that. I had the turbo kit I got for our 96 GTR, Skyline GTR, was an Apex kit, and those were manifolds made you know, by Apex back in the days in Japan, and they were actually coated from them on the inside. And that coating, whatever it is, it's lasted this entire time. It's held up and stuff. I did actually add a external coating to it, and then I did a thermal wrap over it. So I tried to, you know, minimize any of that heat coming out of it. I will say, if you are thinking about doing any wrap, I wouldn't recommend doing a wrap on a manifold that doesn't have an exterior coating, because what I've found in the past is the wraps can sometimes hold some moisture, and then that'll, you know, tend to oxidize and rust up the outside of it. So it's just a shame though, because these things look so good, you know, to coat them,
too.
you know, and that's the thing. I mean, they look so good, and especially if you do a, you know, if after you install it, if you take some acetone and wipe the thing, get all your fingerprints off of it, when it just makes those nice colors on it, you really don't want to, you know, depending on the application, you don't want to hide it. But from a performance standpoint, there's probably, you know, more energy in there if it has a coating and that thermal barrier. So, but yeah, you might be able to get the best of it if you find the right one for the inside. You can keep the outside looking that way, and you might be able to get the best of both worlds. Yeah.
Another thing too with the exhaust wrap is it can exceed the working temperature of the metal itself,
Amen.
depending on the application.
Yes.
Where you want to have at least some air gap. Like some of the heat shielding is a really good way to go, even over coating, where you can keep the heat where you want it to be, but not have that contact of the wrap, and then keeping all of the heat, especially if you have really high EDTs over a long time. That's really hard in the metal. Even like 321 BUs, like you're gonna eventually have a problem if you exhaust wrap it and you don't let it breathe. And so what's nice about it, I like the idea of the inside coating, because it keeps the heat from the manifold all together.
Getting in the metal, yeah. And that's maybe why mine survived and never had a crack or anything, because it had the inside coating, you know, on it. So it might be why I
You
have an issue.
don't always, I mean, when you get to talking about wraps and coatings and stuff, you don't always need them.
Right.
I mean, there are some applications where it's a really good idea, but on most setups, like, you can totally get away without it. On stainless versus like a mild steel or cast or whatever, it actually has a lower thermal conductivity, so it's more of an insulator. It doesn't, I think it's like half or something like that. It's substantial, even though like there's more to it, but it doesn't radiate as much heat as a steel or cast or iron or whatever would. Kind of holds it a little bit better.
Another question?
Not to mention we have an oil failure, it turns into a handle.
Yeah,
Or just
that is true.
glitter.
Yeah. Yes.
I had two people ask me a question. They want you to cover it. The first one is, what is the divider for in the collector on the stock replacement one? And the second one is, are we ever going to do billet collectors?
Okay. So the divider in the stock replacement manifold on the DSM one, it's not a divided setup, but it's a, you know, like on the factory cast manifolds, you have that little factory flow guide vane, I guess. I don't know what it's called, but it's called a flow guide vane, where it actually helps the runners turn.
That manifold is such a flat, plain manifold.
Yeah.
So if you didn't have that there, there's no part of the flow that's hitting down.
Hits a wall.
Yeah.
So it helps guide that flow into the turbo itself, and it seems like some people have taken that off and noticed that it's like a little lazier. I don't know for sure. It's all just anecdotal, but that's what that's for. But on ours, so with the factory DSM manifold, we didn't approach it for a long time because those flanges are like so close, and they're actually angled towards each other. So if you want to have a actual merge collector, you can fit it, but you, like runner number 3, like would just immediately run into it. So what we had to do was angle that collector back to give room for a nice full bend off runner number 3 specifically, to be able to route around it and back up and have it so everything has a really nice guided angle of entry. So when we did that, what would happen is those two of those runners would run into that, you know, the volute on the turbine housing. It's tapered, and then angling it would run into that basically. So what we needed to do was put a flow guide vane built in and welded into the collector to straighten that flow back out and have it go straight back into the turbine housing. So everything's pointed at the turbine wheel instead of, you know, at the wall or whatever else.
Gotcha.
So once all that worked together, and we wanted to make sure to test it, and luckily, like, it worked out, so then we offered it. But that's why that divider's in there. There might be some other effects too, with like a 4-2-to-1 type effect, and I think there's something to that too. But a lot of it's just to correct that flow to get everything pointed where it should, and not at the turbine housing or not at other runners or things like that.
And then what was the other question?
Billet versus.
Yeah. Are we ever going to offer billet?
So billets and cast collectors are great, but we have, I don't count them up. We have so many different applications.
You couldn't buy one collector that's going to work in all your manifolds.
Right.
basically.
You'd have to sacrifice some of the packaging. We were talking about wastegates, like on that one, the wastegate's not centered. Like on a lot of the cast ones, and it works out for most stuff, especially if you're just building one for your specific setup. If you can do it by all means. Especially trying to figure out the angles and weld one up. We've just put a lot into getting that just right, where it just works great for us. But we have all these different style collectors to take advantage of all that space available, whether it's the merge angle or the wastegate provisions, or on the V-band stuff where we can tailor it to each individual V-band flange for each V-band turbo. All sorts of different stuff. So there's a lot of things where each collector is just slightly different, where a cast collector, like, we couldn't cast all those collectors.
Gotcha.
Or even billet options, like just having that many different collectors, by all means, but just what we've been doing actually works really well for us, especially since each manifold is damn near like for each person's setup.
Gotcha.
And we'll change little things depending, if we can get away with it, or if it's something that needs to be changed, like we'll just do it. So, and we like that freedom, basically.
But you can't argue with the results.
Yeah.
If it makes more sense for us to do that, we'd be doing it.
Gotcha.
Nothing wrong with them though. We do like them. It would save so much time.
Anything else you want to hit on, or?
I'm blanking.
Okay.
There's a lot, I'm sure, but
I know.
I'd have to have a little start.
Any questions you guys have? Anything else you thought about? Wonder why it's done one way or another?
Yeah, one more question. do you ever consider making this an Inconel tubing? All Inconel?
Something we thought about, and something where if you wanted to wrap it directly where it's still gonna hold up just fine, you can do whatever. It's so cost prohibitive that it's also just not necessary. Like, it's even the 304 that we've used, you're not gonna notice a difference unless it's like one of those applications where it's like road race, really harsh conditions. So 321 is even like beyond what's necessarily in most cases, where Inconel is even but beyond that, and then you'd have to have a specific Inconel.
Hold on.
We'd have to do specific Inconel flanges and just go down the whole, like,
You're talking a $10,000 manifold at the end of
I
this,
mean-
probably.
maybe, but like,
Just not the benefits there for most people.
it'd be nice, but
Yeah.
few and far between for when it would.
Yeah, I
So-
see a lot of people using on road racing like time tacking because it's all, they want to save the most weight and they also want to,
Like F1 stuff,
control
I think
the temperature
yeah.
much better.
Yeah, temperature wise, I'm not sure. Typically they use Inconel to go with a much thinner wall tubing to get much lighter weight, and where weight is like a really big factor. Whereas, we'll use the thicker wall stuff because, it's not that heavy, and like having an issue with reliability would be the worst.
Right,
So-
right. So, just so people understand some of the difference in the different stainless grades, there's 304, there's 316, there's 321. Would that be the mix of what most people are going to counter?
Yeah.
Okay.
Like typically 304 and 321. The 316, I think this main thing is strength is like salty.
Okay, just the corrosion stuff.
Corrosion.
Okay. So it's going to be basically 304 or 321 is what most
Usually,
people see. Have you noticed anything with the material? I'm sorry. On the, I'm looking at this. You're using a stud on the turbo inlet flange. Have you noticed any particular materials that work well? Have anybody used titanium studs there versus stainless versus just a regular steel? Have you seen any problems with the one or the other?
there can be. So we always include the hardware to those
Okay.
because it's a stainless flange and it's threaded, which allows us to, not have to worry about a nut on the other side. You wouldn't even be able to, anyway. It's a stainless threaded flange. If you were to use a stainless bolt,
It's going to weld itself in
Yeah,
there?
it could. There's a much higher chance of it galling and getting seized up in there. So we have a really high grade, but still steel, not stainless, stud. And then the nuts that are on there are again stainless steel, just because it's a dissimilar metal.
Gotcha.
So like what Robert was saying too about the steel and steel stuff, when those contact, they're more likely to fuse.
Right.
So on this, we always go with dissimilar metals, include this stuff. You can use titanium because it's not, but if it's stainless, just stainless.
Just avoid stainless.
Avoid it, especially with the heat that's going to see.
Gotcha.
It just comes apart so much easier just using that.
Good to know.
And 347 is another manifold material that works well too. It's on par with 321. It's just a different alloy.
Gotcha. Is there, does the 04, the 16, the 21, the 47, is that referring to a specific amount of an additive in that stainless?
I think it's the alloy that they use. Like 321 uses titanium as the alloy to raise its heat resiliency. Or
Gotcha. Because like with steels and stuff like a 1018, you get 1.8% carbon. You got 1050 to 5%. Whatever.
I think
it's nothing like that though. It's not like a specific amount of one thing.
I get this all wrong trying to quote anything, but I know that it's stainless for 321. 347. It's just the extra alloying material to add that heat resistance, basically.
Gotcha. And so 321, is it magnetic at all? It's not.
Nope. Nope, neither.
Any other questions?
Road racing applications.
Road racing application?
No detriment, yeah.
No detriment switching from a cast manifold to a
Using this road racing gonna go.
That's, when 321 was less available, that's what we kind of reserved it for was road racing applications where you knew there'd be extended duration, higher heat stuff, you know, where it's gonna be at a higher working temperature. And now we just use 321 across the board because we can. So it just covers that off the bat.
So other than the weight, we would be fine running it on.
Well, you know,
It still
your big-
depends,
yeah,
but I mean,
your biggest problem and biggest mistake people make, biggest reason why one of the biggest problems that I see out there is I'd say about 90% of the professional tuners in the industry suck. Maybe it's 95.
No, that's a lot.
And among those, I call it the Forrest Gump school of tuning, and that's the rich and retarded. You know, they think that a safe tune is a tune that's rich and that it has retarded ignition time. Oh, I'm only running 10 degrees. Really, that's it? Well, you've just created an afterburner effect. Your EGTs are probably through the roof because they're probably not even monitoring it. The right amount of timing, there's no such thing as a safe tune. An engine has the proper tune or it doesn't. And that's the whole thing. A lot of people, when they do these safe tunes, they're not running enough ignition timing. They're running it too rich, and they're putting all of this energy right into the manifold. And you put too much heat in there, and you can't get that heat out, things are going to crack, things are going to break. And that's usually what it is. It's 9 times out of 10, the tuner doesn't know what the hell they're doing. And it's worse now that direct injection engines are out there, which take a whole different timing curve. And it's really pretty bad what we've seen out there. But,
Or the customer doesn't. We get a lot of, we just want the pops and bangs.
oh God, yeah,
Give me the pops and bangs too.
yeah. That's
Yeah.
not good. Not good for your valve drain. Not good for your exhaust manifolds.
Okay.
Or do you want to add anything like that? Have you seen? Is your stuff tough enough to hold up to stupid tunes?
we liked those applications because it kind of like, you know, if
It
holds
showcases
up,
that it's like, yeah.
just that extra peace of mind for everyone
Gotcha,
else.
gotcha.
And there's a lot of, I mean, we love to see it on road race stuff where they're gonna really push it hard, just
Mhm.
just to know, just to see. And we do have a few out there.
We got about 10 seconds left. I think you're out of storage. That last one gave me 7 minutes.
Oh, really?
Yeah.
Oh, cool. Well, we're good then. That means we're done. Awesome. I'll switch the card though.
Yeah.
Just in case you got anything else.
Yeah, it says 15 seconds. Like,
Oh, wow. That's good. That's like perfect time. And once I switch to these batteries, like, it lasts forever. Pretty cool.
Is there a little bit just to add?
Yeah, yeah.
Whatever. I mean,
No,
Yeah.
we switch cards now. Keep going.
So I guess if people are interested in finding, we've been a part of some pretty cool testing over the years, and we have a lot of the tech articles on the website, and also we also had like what a turbo manifold actually does recently to kind of, and we're going to be building on top of that. We're even coming out with more articles, write-ups. Again, talking about the cylinder-to-cylinder interference, length, sizing, different setups, wastegates, all this stuff. So we want to build on top of that. But we also have like a bunch of back-to-back dyno tests for small, large, stock replacement versus FP race. All that stuff's on the website on the technical article section. Something we want to keep adding to.
Perfect. And when are you guys gonna clone yourselves or get more people there so you can make more manifolds quicker?
I haven't figured that out yet, but it's just gonna be Samantha and I, and that's how we want to keep it. Just to, you know, I know that, you know, it's not as high volume and stuff like that, but like, it's just.
The quality part is important to
Yeah.
us, and we get to like really keep hold of what
It's-
we're doing.
It's tough when you're offering a custom product to every person, and which is essentially what you're doing. You know?
Yeah.
I mean, we're kind of in the same. I understand what you know, at the machine shop, you know, doing the engines and stuff. even though as much as we'd like to have a package A and a package B engine, so we could just do 5 of them at a time, everybody wants one thing different, or this guy's bringing you this part to you. So it's a nightmare. I understand. I share in that nightmare, but I also share in the joy you get in helping out that one customer get exactly what they want.
Keep it personal. We
Yeah.
don't want to dilute it.
Exactly.
And keeping the relationship,
Mhm.
right? Like we love like becoming friends,
Right,
you know, and
right.
like keeping updated. And
That's cool. That's cool.
but if somebody wants to come bevel ever, please.
Prep work. Yeah.
Right.
It's not just welding.
So there you go. So if you get that
Yeah.
guy in there doing the prep all the flanges, do all your tumbling or whatever you got to do, all that stuff. Ugh, that's the not so fun stuff.
Oh my God, I hate it.
How much time, just off the top of your head, like percentage wise, how much time is spent
Just prep.
cutting the pieces, putting the pieces together, and the actual welding part? Like, how does that break down?
So there's at least 2 hours into just the prep work, where it's
That's
just
it? You sure it's only 2 hours?
Well, we've gotten
Just
pretty
the
good at it.
Runners.
Yeah.
Work, not like the.
Well, we don't tumble it or anything anymore.
Yeah,
we have that out.
tumbled,
Okay.
and then to get the nice finish to begin with, and then finish off.
But like just the cutting and the beveling, we've gotten pretty good at it.
Do you have like jigs or anything so that you know exactly, like, is this in your, do you have a catalog that's piece A, B, C, D, E, and you're cutting all those and do you know what to put together, or are you
Kinda.
Yeah.
kind of building it as you go along?
It's
Sometimes.
So every job is custom, basically.
Basically.
they use like a lot of them. They'll have like a build sheet that has like what bend
Right.
bend is and what the straights are.
Right.
But you still, and then everything pretty much lines up from there. You might still have to tweak it something slightly, or like when things route really close to each other. Like
Right.
there's a lot of time in making sure things are just right. Where like it's snaking through another, or like trying to make the most out of the space available, or like for that, like depending if it has a 2G water pipe which sticks out a little bit more and it's down further, you want to make sure that one runner doesn't require it to be dented, or if you have that 1G engine mount bracket, to make sure that the bend
Are
is
you
just above
actually
it.
building it on an engine block and head? Is the flange up in there and you're doing it?
Sometimes there's some back and forth depending on
Okay.
we have all these different alternators or
Right.
power steering pump or just all this stuff, because it's just having it itself
Mhm.
versus trying to make fixtures for everything just doesn't work. So we just we can work around it and know ahead of time instead of having any surprises. I mean, it still sometimes happens, but we try to think of everything.
Now, one of the things I've seen is, when you're buying U-bends or J-bends or anything like that, sometimes, depending on the quality of what you're getting, when you cut it, it's different shapes. Sometimes the lower quality stuff, you're cutting it and it's oval instead of round or whatever, right?
Yeah.
Do you ever see that?
Sometimes, and we'll go in and fix it,
Mhm.
because sometimes throughout the casting of the elbows, it's not as exact as the ends.
Okay.
So we'll go in and massage that, but it's usually not far off. It's just far enough off where when you go to weld it and you have the points meeting, you
Mhm.
can't have any gap there, have any where the argon can come out and affect the weld pool. So it's just there's some little stuff like that for sure. But as far as, we do have a bunch of fixtures and jigs for cutting everything, especially the collectors, to make sure that everything's the exact right length, the exact right angle,
Mhm.
the outlet size, because you want to match the flange and have a really smooth transition to it. A whole bunch of stuff for that. We have I think something interesting now for modern manifolds, you'll
Mhm.
see a lot. But back in the day, they used to only use 45s and 90s because that's the only way you could get them, and you didn't have a consistent way to cut the elbows themselves, where you didn't know, like you could cut it at like 60 degrees, but who knows if it's over
Right.
too far this way. So now they have, like PRL has these nice cutting fixtures where it sits in there exactly, you can cut exactly where it needs to be cut, and then you have this gauge to know you can set it like 65 degrees, and it's 65 degrees every time. So you can
Nice.
reliably build a manifold based off that, instead of like having to mess around with this so much. Like back in the day you couldn't, so like you notice that all these manifolds only use 45s or only use 90s, and now you have those cutting fixtures where it opens up all these possibilities where you can have more integrate routing, and instead of we can't do this routing because it can't work with just 90s and 45s, now you can do whatever you want and just it gets, I mean, it's more work to it, but you just open up possibilities fabrication wise.
Very cool. And one of the other things we were talking about was the flange, and typically when you weld something,
Oh yeah.
it's metal's going to be pulled this way and pulled that way, and kind of what you're doing on the flange, so that it's not having all these residual stresses stored inside.
Yeah.
You actually have a fixture or a jig that actually kind of pulls it the opposite way that it's going to want to pull once
Yep.
it's welded.
Because during
Gotcha.
welding, that's when you want to try to fight it from moving.
Mm.
But if you try to like fix it afterwards, it's strong. But yeah, there's like, and we have a ton of things when you're welding, like things move, especially stainless, and it pulls things all over the place. And like everything we weld practically will have, flange-wise, will be bolted down to an aluminum heat sink to suck the heat out of it, so it doesn't have as much of a chance and keeps things rigid. Just all around, just a great option. Like we have so many different types of heat sinks to keep everything true. So there's much less, like we deck everything afterwards, but there's just so much less you have to take off to get everything perfectly flat. And then the welding processes on the head flange, like you were talking about, we have different processes for when you weld the outside of the flange, it's gonna try to move this way. When you inside weld it, it's gonna move back. So on a lot of the stuff, like you have to really keep in mind where it's gonna end up in the end, and how much heat input, and like things shrink or.
Right. So you got to have a procedure, welding in the right spots at the right time. It's not like you just start here and you're just going to finish number 1 and then go to number 2. It's the whole process of.
You could have a mess if you
Yeah.
don't think about it. Or even, get into a lot, but even like the order of welding the runners to the collector themselves. If you do it in the wrong order, there's one, if you try to do the wrong runner last, you won't be able to access it. Like it's hard enough to begin with, where you have to have a bend constant like 90 degrees or even more just to reach around that corner to get the arc to it. But if you, that's even when you do it right.
Right.
And if you do the wrong runner last, like you just had to chuck the whole thing because you wouldn't, like that's never happened, but
Yeah.
it could.
This would be my building my own manifold would be a nightmare project. That would be like a sentence to hell for me, I think, if ever anybody asked me. There's so many things that could go wrong during the process. I mean, even if you knew the exact lengths of everything, I mean, there's just
it's great to do though. Like you will find so many things that you would change. Like the first time you do one, even when we design a new one, like there's little things that we like think like once it's all together, like maybe we can do this a little bit differently next time.
Like even this one has been redone like 12 times.
Yeah, the placement, like
Just last week.
The turbo's like larger, like the G42 1450, like the compressor cover got a little bit bigger. So like
Hold on.
So like that was originally, the sheer top mount was designed like when he was doing it around like a GT42 turbo. But now the newer TurboTech, the G42, like it's a little larger compressor cover. So to account for that, we move it down and over a little bit. So we had to like refixture everything and have it all modular in case everything changes again. But just those slight changes to make sure there's that good clearance. There's a lot of sweating over that stuff.
Do you serialize them? Does anybody know which one is for what, or no?
First of all, that's a good idea.
It's a good idea. Usually we can tell. Like it's kind of cool to be able to look back and like see like the weld line on a certain
Right.
one and kind of idea it that way.
Because it'd be interesting, if somebody ends up with one of your manifolds that was for the earlier, sheer top mount, and now they want to put on the big stuff. It's like,
can
okay,
look.
is this gonna work or not?
It's cool seeing the older stuff that we have because we used to hand engrave all the head flanges
Oh, you did? Okay.
by hand with their hands in a Dremel, and it turned out like not a lot of people would know that looking at it, which was cool. But now they're all CNC'd and everything's engraved, and you don't have to spend an hour like doing other stuff to be able to get your hand to work again. But yeah, just seeing like the hand engraved flanges is pretty cool.
Okay.
Floating around, and I don't know, I like that.
Any other questions, guys?
Do you ever purge the inside of them if you do have a gap, when you're welding them?
Always purged.
Always
I mean, there's
purged.
some instances where you don't. I would just say always purged, especially on stainless where it's so reactive. Once it's like a molten weld pool, like it's gonna react and just
Yeah.
bloom out and get the sugaring and granular corrosion, all that stuff. Yeah, that's a big thing for sure. And then always having no gaps is really important too.
Oh, yeah.
If you have a gap in a purging, like that gap is going to shoot argon back at you or at the torch, and it's going to get a really poor weld, and you'll see it just kind of everything
Yeah.
kind of go awry.
Yeah.
Or if you have a gap, like that gap's going to close. So if you had everything just right and like had a little off center, like I'll just tack it and then weld it up and it'll be fine. Like no, all that's going to go back, and it's going to be off. So.
Well, thank you so much. Appreciate it.
Thank you.